Okay, so this is before the equivalence point. So the first thing we need to do is a Bca chart to see what we have left over. So what is actually reacting here is the weak acid and the hydroxide ion are reacting together to make water and the acetate ion. We use molarity equals moles over liters to find the number of moles of each. In Bca charts, we always need to use moles. So even in the previous example, we know it's 0.00525 moles of acetic acid. Using this as the volume, we get 0.005175 moles of OH minus that we're adding, and we start out with no moles of the acetate ion conjugate base. Now we use up all of the base in a titration, so this guy will go down by 0.005175. At the same time, that amount will need to come out of my acetic acid. Those two will react together and make 0.005175 moles of acetic acid. There will be no base left over, and this is a very small number, 7.5 times 10 to the negative 5 moles. So now that I found out how many moles I have left over after all of the base that I've added is reacted, I divide by the new volume to get the new molarities, and it's those new molarities that I can use in the Henderson-Hasselbalch equation or an ice chart. So it would be 7.5 times 10 to the negative 5 moles, and then the 35 milliliters plus this 34.5 liters is 0.0695 liters, right? So the molarity of my weak acid is 0.001079. I do the same thing with my conjugate base. And that equals 0.07446 molarity. So this is the molarity of my weak acid and its conjugate base. And now what I can do is put those together in an ice chart or use the Henderson-Hasselbalch equation to find the pH. So the weak acid reacts with water, donates a proton to water, H3O plus and CH3COO negative. I'm using my initial concentrations from the previous table. Water we don't care about. Right, minus X plus X plus X, 0.001079 molarity still, and 0.0446 molarity. The Ka for acetic acid is 1.8 times 10 to the negative 5, and that's equal to X times 0.0446 over 0.001079. X is equal to the H3O plus concentration. Turns out to be 2.60 times 10 to the negative 7, and the negative log of that will give us the pH, and that is 6.584. The same thing you get if you just go right straight to the Henderson-Hasselbalch equation. So before the equivalence point, and this is even just before the equivalence point, what a half milliliter before it, we're still at a pH below 7. The next one that we are doing is the pH at the equivalence point. And this one is tricky because at the equivalence point, we've used up all of the base and all of the acid. All we have left is conjugate base. So that's really what we need to do the problem with. The next type of problem is the pH at the equivalence point. When we're at the equivalence point, the moles of base that I've added is equal to the moles of weak acid that I started with. So the only thing that's actually in solution that could affect the pH is the conjugate base. So I basically need to do an ice chart with the molarity of the conjugate base and the Kb. So just as a, just to sort of do the same thing every time, if I take, right, this is what is the reaction that's going on. The the strong base, the OH minus, is reacting with the weak acid. And if we take the molarity times the volume, these are both 0.00525. And then they would both go down by 0.00525. And that would mean that at the equivalence point, the concentration or even the amount of moles of those is 0. But this guy will go up by 0.0, yeah, it is 0.00525. So 0.00525, that's my moles of the acetate ion, the conjugate base. And now I divide that by the volume. 35 milliliters and 35 milliliters is 70 milliliters, or 0.070 liters. When I divide those, I get 0.075, and this is the molarity of my acetate. So what is actually going to be reacting in solution is the acetate ion, right? It reacts with water. It's a conjugate base. It takes the hydrogen off of water and leaves behind OH minus. That's why we're going to have a basic solution. This is an ice chart here just to keep us organized. And now I can't use my Ka because Ka is for acetic acid acting as an acid. This is the acetate ion. So I use the fact that Ka times Kb equals Kw. 1.8 times 10 to the negative 5 times the Kb equals 1.00 times 10 to the negative 14. And the Kb for this acetate ion is 5.5 times 10 to the negative 10. What is that equal to? Well, x squared over 0.075. So x, which in this case is the OH minus concentration, turns out to be 6.45 times 10 to the negative 6. Take the negative log of that. That's the pOH, and that's 5.19, which means that the pH is 14 minus that, or 8.81. And that's very typical of the equivalence point of a weak acid being titrated with a strong base, because at the equivalence point, the only thing that should be in that solution is that conjugate base. So now we're after the equivalence point. And when we're after the equivalence point, the calculations are actually fairly easy because we have no more weak acid, and the conjugate base is by definition pretty weak. So the only thing that's really affecting the pH is that excess OH minus that we add. I like doing these calculations still with a Bca chart to calculate that number of moles of excess base. So if I do a Bca chart, right, with the reaction that happened, the acetic acid reacted with the OH minus to make the acetate ion and water. In a Bca chart, we work with moles. This was our 0.00525, and taking this, molarity equals moles over liters, I will have added 0.05325 moles of OH minus. These guys, of course, would be 0 and water we don't care about. Now we subtract, and what gets used all up is the acid, right? So minus 0.00525. Minus 0.00525. You can do plus 0.00525, but we need to recognize that this amount of conjugate base, knowing that it only dissociates, look at the Kb for this, was very small. That is not going to factor into the basicity of this solution. When I do this subtraction, I get 7.5 times 10 to the negative 5. And what is that? Well, that's moles of OH minus. I take that moles of OH minus and divide by the new volume to get my molarity. Right? This is going to be 70.5 milliliters, or 0.0705 liters. The molarity is 0.00106. What is this the molarity of again? The molarity of the OH minus. So when I take the negative log of that, I get the pOH, and that's 2.97, which gives me a pH of 11.03. And that makes sense. I'm past the equivalence point now. It should be very basic. The last calculation here is well past the equivalence point when we've added 15 milliliters of base, so much to an excess. The answer to this question, the pH for this is 12.42. Again, this is the exact same type of calculation as you did previously, as we did with the 35.5. You just need to do it again, but this time with different numbers. So I will pause here, do out the problem, and then check to see if you actually get 12.42. Okay, I'll do it out right here though. So we would take our weak acid, we are going to add hydroxide, and we are going to make the conjugate base, or we're going to leave conjugate base left and water. BCA, we start out with our 0.0052 moles of acetic acid, and molarity. Molarity times the volume for the OH minus is 0.0075 moles of OH minus now. So when I subtract 0.00525 minus 0.00525, of course there's no weak acid left. I'm well past the equivalence point, and there is 0.00225 moles of OH minus left over. Molarity equals moles over liters, 0.00225 moles of OH minus divided by our total volume, 35 plus 50 is 0.085 liters. The molarity of the OH minus is 0.0264, which means the pOH is 1.57, and the pH is, as expected, 12.42. Very high, because we are well past the equivalence point.